So in this video, we're going to introduce the minimum spanning tree problem. So before I explain what those terms mean, let's start with an example. So suppose your friend works at the electric company and wants to figure out how we can give power to all of the cities she needs to serve. But she wants to, save money and not want to spend like a bunch of extra money on unnecessary connections. So suppose your friend knows, we're supposed to serve these cities A, B, C, D, E. Suppose she knows what's the cost of laying wires between any two cities. So she might know that the cost to lay wires between B and E would cost something like $2 or $2 million, whatever scale of money you want. And maybe that's a low number because they're close together. But then maybe like C and E might be really, really far apart. Maybe there's like a mountain or a river in between. And laying wires between those cities would be really, really expensive. Now, what your friend's goal is to make sure that every city receives power, but to make sure that the wires they lay down cost as little as possible. So they want to save money by laying as few wires, or in some sense, laying the cheapest set of wires possible. So we're going to make some assumptions here about how this is going to work. We're going to model this situation as a graph where all of the vertices are cities and our electric company. And all of the edges are these like possible costs to lay a wire between these two entities. So in this graph example, to lay a wire between the electric company and E would be $9 or whatever. So we're going to make some assumptions here about this graph. This is kind of all the possible wirings we could use. All of these costs we're going to assume are positive. We're not going to assume there's any like government subsidies or anything like that where you like get money for laying wires down. We're also going to assume that the graph is going to be undirected. Why? Well, if you're able to lay wires between B and E, it should also make sense that you could lay wires starting from E and go back to B. So in this example, we're just going to assume this graph is undirected. And we're also going to assume that electricity can travel through cities. What I mean by that is that you don't need a direct edge from a city to the electric company. So for example, one way of powering city A is instead of having an edge directly to the electric company, you can have an edge from A to B and then from B to the electric company. So we can like let electricity travel through a city so that we don't have to have these direct connections to our source. So we have this graph of possible options. How can we go about choosing what set of wires do we want to lay down? So to kind of formulate this problem in graph terms, our solution is going to be a set of edges. So we're going to choose from this, all of these possible edges, we're going to choose a subset of them. So we're going to choose a set of edges such that the graph is going to be connected because we want to power every city. So we're going to say that this set of edges should span the graph, that every vertex touches at least one edge. But that's not enough. Spanning the graph is not necessarily going to give you connectedness. So we do want this graph to be connected so that any city is connected somehow to our power company. And we want this set of edges to have minimum weight. So we want this set of edges here to be the cheapest set of edges possible so that we save the electric company money. So here is one example of one of these sets of edges that hopefully have this minimum cost. So I want to make an argument to you about any set of edges that are going to satisfy this criteria. I would argue that we would never pick a cycle. So there's no graph you can come up with where the minimum set of edges would form a cycle. Now, why is that? Well, first, the minimum number of edges you would need to kind of cover the graph would be v minus 1. You can imagine if you have these v vertices, you would need v minus 1 kind of links between them to make sure they're all connected. Now, if you were going to add an extra edge to go from maybe C to B. Maybe we'll say this is cost 2 or something like that. This is only going to strictly increase the cost of the solution, and it doesn't buy you anything. Remember, our big goal here is to just connect all of the nodes, and we want those edges to have minimum cost. If we already had something that was acyclic that connected everything, and then suppose we added another edge, that would form a cycle which would increase the cost of our solution because all the edges have positive edge weights, but it didn't further connect the graph. It was already connected. We just added an extra edge for fun. And I would argue too that this is going to be true anytime. Anytime that you would create a cycle, that doesn't further connect the graph, right? If you take an acyclic connected graph, add an edge to make it cyclic, well, it's still connected like it was before, assuming it was connected before. Now, if it was disconnected before, adding that edge may or may not add a cycle, but assuming we kind of already have this connected graph, there's never going to be a case where we want the extra edge. So the other kind of property here is if you ever had this cycle, you could always just take away one of those edges and the graph would still be connected. Now, this isn't true if if the set of edges you chose is acyclic, right? If I went through and took out this edge, well, now I've disconnected the graph. So this is really only true of being able to remove edges if there's a cycle. So that's kind of one of my key claims about kind of one of the properties this problem's going to show. And now that we kind of have that kind of framework that we're not going to have cycles under our belt, now I can start actually introducing some terminology that we're going to use for this problem. So if we think back to what we've seen before in this course, I talked about this idea of a tree. And so far, I've always told you trees are like node structures with parent-child relationships. So I said, for example, in lecture 9, a binary tree is a collection of nodes where each node has at most one parent and anywhere between 0 and 2 children. And then I told you about the idea of a trinary tree or a quadary tree. And I even for B trees talked about M-ary trees. And each one had to have its own special definition for the number of children it had. Now, I would argue that there's actually a much more general notion of a tree that kind of fits into the graph terminology because graphs or trees are just special cases of graphs. So we actually use the term tree more generally when talking about graphs. So we're going to say a tree is a collection of nodes connected by some edges where there's exactly one path between any pair of nodes. And so I've shown you some other graphs here that are trees. You can imagine kind of drawing them out in the right order. So one's at the top, and then it has their children below, and then the grandchildren below that. But graphs don't really care about how they're drawn. They're just nodes and edges. And so this tree is a much more generic version of talking about parents and children. Where that comes from is there's exactly one path from one node to another node. So here are examples of some other trees. Here I have a tree with, this one has 3 children, and then here. Now this tree doesn't necessarily have the rigid structure that a binary tree does, or it's saying like, oh, it has at most this many children, but this is a tree nonetheless, or at least fits our definition, this more general definition. There's also some examples of graphs that aren't trees. For example, one with a cycle. There are multiple paths from one node to another. And also a disconnected graph is also not a tree because there's not a path from, say, this node down here to one of the other nodes. So it turns out that all trees are going to be connected acyclic graphs, right? Any tree that's, if something's going to be a tree, it has to be connected because you need to be able to get to any vertex from any other, and it needs to be acyclic. Cycles allow kind of choice in which path you might take. And we kind of said in this definition of a tree, there should only be one possible path. So this now changes our problem a little bit. Instead of finding the minimum set of edges, we're going to find the minimum spanning tree. And that's where the name of this problem comes from. We're going to find a set of edges that forms a tree that spans the whole graph. And we want this tree to have minimum cost. So it's the same setup essentially as before when I was saying find this minimum set of edges, but I'm just being a little bit more particular that this set of edges is going to form this thing called a spanning tree. It connects the graph. It's going to be acyclic, and we're looking for the spanning tree that has minimum costs. So there are potentially, if you think back to that original graph of with the factory or the electric company and all of the cities, there are lots of trees in that graph. Remember, in this problem, we're choosing like a subset of the edges to use. You could choose lots and lots of possible subsets. So lots of these subsets could be spanning trees. They form a connected acyclic graph that spans all of the vertices. So here's an example of one such spanning tree. If you add up all of its edge weights, you get something like 33. Our job, kind of to help our friend at the electric company, is we want to have an algorithm that kind of searches over, in some sense, all spanning trees and finds the one with a minimum cost. So in this example, this solution I showed you earlier is going to be the minimum spanning tree because it has cost 16. Both of these are spanning trees, connected acyclic graphs that touch all of the vertices, but this one on the right is a minimum spanning tree. It has the minimum cost. And again, do remember that we're kind of, these edges that we're using for our spanning tree are like choosing edges, a subset of the edges from that original graph. Now, we're going to talk about algorithms to do this. We're not actually going to enumerate all possible minimum spanning trees and then find the minimum. There are going to be algorithms that let us do this efficiently. We're going to talk about one such algorithm in the next video. But to just practice this a little bit, I want to give you a graph, and I want you to tell me what is the minimum spanning tree for this. So all I'm going to have you do is enter the cost of the tree. So find the minimum spanning tree and of this graph, and then tell me what's the cost, what's the total edge weight for that. So take a second and try this out. Okay, so hopefully you had some time to work on this. So what I would say is we need, remember, for our kind of minimum spanning tree, we need this thing to be connected. Try my best with the mouse. We need it to be acyclic. And we need it to span the graph. So there are lots of possible edges here. There are 4 nodes, 4 vertices. And so kind of using that argument I used before, we know there are going to be 3 edges, b minus 1 edges. Now, if you're doing this kind of by hand, we don't maybe have a principled approach for doing this, but I know that this edge right here has to be included in the minimum spanning tree. Why? Well, because there's only one edge that connects C. So any minimum spanning tree, because it has to connect to this graph, needs to include this edge. And so then it's kind of a toss-up here. For, I could include any 2 of these edges in some to connect everything else to D. But what you might have noticed is I would choose A to B. Now, this might be, and then the cost of this would be 1 plus 2 plus 3, which would be a total of 6. That's the cost of this. And, because this graph is so small, you could technically enumerate all of the spanning trees, all subsets of edges that connect the graph that are acyclic. And you'll see that this one is the one with minimum cost. Now, this is just getting you to practice what is the idea of a minimum spanning tree. In our next video, we'll talk about an algorithm to find it, and we're going to talk about some key properties of these minimum spanning trees that kind of hint at how an algorithm will go about trying to find these things. But talking about how to do this generally with larger graphs, that's the focus of our next video.